Okay, the next and the last speaker of the day is Prasuna Bandi from IHES, France. She will speak on exact approximation in metric measure spaces. Prasuna.
Thank you. Yeah, I would like to thank the organizers for the this conference and also for the opportunity to give a talk. And I also would like to wish Professor Dani a very happy birthday. And thank you for all your great contributions to the field. Yeah, so yeah, let me just start my talk. Yeah, so today I'll be talking of this whole work is joint work with Anish and Burgeand. Okay. Yeah. Okay. So we have seen in many talks, starting with Dirichlet theorem. So I would also need this, but I will not recall it here because we have seen it many times already. So let me start with something called psi approximable set. So for a decreasing function psi, from R plus to R plus, define set of psi approximable numbers to be elements in R such that mod x minus p by q is less than psi of q for infinitely many rationals. Yeah, for infinitely many rationals. So this comes from the Dirichlet theorem. I mean, it's related to it. When psi of q is 1 by q square, Dirichlet implies that corollary of Dirichlet theorem implies this set is whole of R when psi is 1 by q square. So, and then Khintchine proved that if the function x mapping to x squared psi x is non-increasing, so this is by Khintchine. The Lebesgue measure of the set W psi, which I denote by lambda. This is 0 if the sum converges, summation psi of q is finite. Sorry, this is mod x minus p by q, so we get q psi of q. And its full Lebesgue measure or 1 if sum diverges. So we have this nice 0-1 law. And then the question is about, so now we have the Lebesgue measure statement, which is 0 whenever the sum converges, and it doesn't differentiate between different sets where the sum converges. So we have the Hausdorff dimension result to differentiate that. So this is proved by Dodson. So I mean, all these conditions are sort of can be improved more. They have been improved later, but it's not that important for now. So I'll just write whatever they have proved. Yeah, let this be a decreasing function. And yeah, so here we need to define one notion for a define lower order at infinity of a function g to be limit log gx by log x. So it's just a measure of how the function is behaving at infinity. So for example, if I have g to be the function q square, what it gives is just lambda of g is 2. So what we are interested in the quantity is we define lambda to be lambda of 1 by psi. And then the Hausdorff dimension result says dimension of w psi is 2 by lambda if lambda is greater than 2 and it's 1 if lambda is less than equal to 2. Dodson actually proved this result in for matrix case, like when if a general M and N means here you replace R to be R matrix M cross N matrix, like Iris was talking about. Yes, it's a Hausdorff dimension. So this is, yeah, so this is the Hausdorff dimension result. And then following this, a natural question to ask is to look at those points which are psi approximable, but not phi approximable with respect to another function phi. So we have a function phi and psi, so that phi is less than psi, I mean, in certain way. Then we are looking for points which are psi approximable, which are in W psi, but not in W phi. And so this question has been studied by Beresnevich, Dickinson, and Vellani. So they proved that when psi is when phi is decreasing, I mean both are decreasing functions. When phi is smaller than psi in certain sense, we have this result. So let psi be slightly decreasing and continuous function. So we look at the case lambda is greater than 2. Lambda greater than 2 is a case when the sum converges in the Khintchine's theorem. And let phi be decreasing function such that phi of r is less than psi of r log r, kr. This for some k greater than equal to 1. This is just some notion of saying phi, the rate at which phi decreases compared to psi. So this, in particular, this says that psi by phi, this goes to infinity. And also we need some technical condition on which I will not write here. In this setup, they prove that Hausdorff dimension of the set D psi phi. Okay, so what this is just W which are in psi approximable but not phi approximable. So dimension of this set is same as the dimension of W psi. So we know already. Yeah, this is the definition of D psi. So which are psi approximable but not phi approximable. So even when you remove the points which are not phi approximable, it will still give you the dimension of the full set, W psi here. But so this method can only be applicable when we have the growth of phi is much smaller than the growth of psi. So it's very natural to ask about what if phi gets sort of very close to psi. Like for example, when say phi is some constant times psi, when c is strictly less than 1. So for this, they couldn't give the answer, and this was solved by Burgeand. In fact, he proved a more general statement. I'll write his theorem. What he has actually showed is that he considers the set of functions which are psi approximable and not c psi approximable for every c greater than 1. Yeah, so he considers this set. C less than 1, right? C less than 1. Yeah. Okay. So we define this set as the exact psi. So it's exactly approximable, exactly psi approximable. Yeah, okay. So define E of psi to be W of psi minus so this function, when phi is c psi, so d of psi c psi, it's a very interesting set. It's sort of connected to the badly approximable numbers. Like when you take psi to be the function 1 by q square, this is contained in the set of badly approximable numbers. So giving a bound on the dimension of this lower bound will also give you a lower bound on the badly approximable set. Okay, so I'll write what the theorem of Burgeand. So let psi be such that x square psi x is non-increasing and assume that some summation x psi x converges. So here I haven't defined what lambda is, I think. Did I define? No. So here lambda is lambda of 1 by the function 1 by psi. Okay, I have defined it here. Yeah. This sum converges Then so he proves the dimension of this exact set is again, it's same as the dimension of the psi approximable set, which is 2 by lambda. Yeah, so he also proves it later for the divergence when the sum diverges and there's not so much restrictions on the function side. But this is the first theorem that he proves in this setup. So this is proved by, so this proof is by constructing a Cantor set with nice structure inside the exact set and giving lower bound on the Hausdorff dimension of the Cantor set, which is sort of the usual way these are proved. And he uses continued fractions to construct the Cantor set. Using continued fractions, constructs the Cantor set. Inside the set E of psi. Okay. So what we prove is generalize this to an Alphonse regular setup, which again Alice was talking about today. So before stating the theorem, I will first say what is the setup we work in. Okay, so before, we need some definitions. So I will again recall once again what is Alphonse regular. So let X comma D is a metric space. Borel measure mu on X is said to be alpha Alphonse regular if so measure of any ball is sort of approximate is kind of like r power alpha is less than c times r power alpha, it's greater than 1 by c r. There's some constant c. Then exists some constant c. Such that is. So we need Alphonse regularity, and then I also need to define another notion. So in the general setup, so what takes the place of rationals? So that would be something called well distributed and separated, denoted by WDS. So this is so a countable. So this is the set which takes the place of rationals. So a countable set Q is said to be WDS if there exists a radius function or from Q to R plus such that the following properties hold. So the first I will say what is well distributed is. So well distributed means it has to satisfy these properties. So if there we have there is a radius function and some constant C such that so this notion of well distributed is not really new. It existed, for example, there are different terminologies like regular system, optimal regular system. It was first introduced by Baker and Schmidt to compute Hausdorff dimension of numbers which are approximated by algebraic numbers. So this notion already existed before. For each ball B, there exists a constant only depending on the ball such that for every k greater than or equal to kb, there exists some subset of q depending on k for each ball q one for each element in qk, the radius should be in the range of 1 by k. It should be like 1 by k. So this is less than some c by k and it's greater than 1 by ck for every element in qk. And the union of all balls with centers in qk and radius with respect to the radius function, this is contained in V. And the main thing, see, the third condition is the number of points in qk is greater than or equal to 1 by c k power alpha measure of b. So this alpha is the alpha from the Alphos regularity. So here we assume x is alpha Alphos regular. I'll explain more about these conditions, like by looking at the rationals, how they satisfy these conditions. Yeah, so this is the definition of well distributedness and so well separatedness, right? Okay, so well separated. It just means that all the points in the set Q are separated nicely. So what does it mean? So distance between xi and eta is greater than or equal to some minimum of radius r of xi and r of eta for every xi comma eta in Q. Yeah. Okay. So, so the well-distributedness, so it's basically, so this second condition is basically asking for these elements, which the QK, the elements of this to lie in B. I mean, once those elements are in B, it's sort of, we can make sure that these balls are all contained in B. And the third condition, this number is greater than equal to this, is basically given by the Dirichlet theorem for rationals. So let's look for, in case of rationals, how they are, they satisfy all these conditions. So for rationals, first of all, the radius function, if P by, of R of P by Q is defined to be 1 by Q square. The function coming from the Dirichlet theorem. And so to show the well-distributedness property, the separatedness is very easy to see. So if I have two rationals, P1 by Q1, P2 by Q2. So this distance is was greater than equal to 1 by Q1, Q2, and which is greater than minimum of 1 by Q1 square, 1 by Q2 square. So this separatedness holds. And for the to show distributedness, we use the Dirichlet theorem. So for first, so given a ball, so given a ball, we choose K large enough such that consider the set. So the QK, this QK will be set of all rationals such that u root K by 2 is less than equal to K less than equal to K. Yeah, this set works because if I take, so first we have given an interval, we choose Ki large enough. And QK will be non-empty, and define A to be set of elements in I. No, wait. First, by Dirichlet theorem, we have for every element xi in I, this has a solution. 1 by Q root K and Q between 1 and root K. This has a solution. So, but look at all those elements for which this has a solution for Q lying between 1 and root K by 2. So, like denote that set of all xi, A1. Q between, this has a solution. If we take K to be large enough, we can show that the measure of this set is small. Measure of this is, we can make it less than, say, some constant times cardinality of I. And from here, we can also show that the complement of A1 is contained in so where P by Qs are from other elements of QK. And this will give us the C part of the well-distributedness, because now the complement of A1, the measure is greater than 3 by 4 cardinality of I, and this is less than mod QK, some constant, mod QK by K. So we have greater than k times cardinality of I. The rationals are well distributed, unseparated. So our theorem applies. And okay, I haven't stated the theorem first. Okay, just I'll state the theorem first. So before stating the theorem of these notions of W psi and E psi in the general setup, let me define that. So once we have this well distributed and sub WDS set QR, Q with respect to the radius function R, define W psi QR. So this is the analog of the psi approximable numbers. So to be the set of all x in X such that distance between X and Xi is less than psi of R of psi. So our function psi and the function that Bourgeois takes in his theorem are sort of different because this is a function of the radius there, which is 1 by q, and there it's a function of q. So this happens for infinitely many xi in q. So this is the analog of well approximable numbers, and define this is the analog of exact set to be W psi QR minus W of C psi QR. So we need C less than. Yeah, okay. So now the theorem in the general setup says, so let x d mu be alpha alphos regular and we need one more condition. It is that all annuli should be non-empty. So for every small r less than capital R diameter of x, so we define this is the annuli with center xi and smaller radius and the larger radius. So all annuli have to be non-empty, and so let QR be WDS. Then and let psi be such that psi of x by x is non-decreasing function and And we need to assume the convergence part of the sum. So that will be analog of that will be summation A in RQ is all psi of A by f of A power alpha converges. Yeah, so this sum converges. Okay, I haven't defined what f of A is. So for A in RQ, so this is the image of the radius function. F of A is defined to be supremum of R such that set of all balls where this eta for the with centers eta where etas are such that R of eta is equal to A. So this set is disjoint. I mean these balls are pairwise disjoint. Yeah, so this is the function f of A. Now here then the dimension of the exact set, so E of psi QR is same as the dimension of W psi QR, and this is this is alpha by lambda of psi. Okay, I'll denote lambda bar because the lambda which I have defined before is for those functions psi. So these are kind of a bit different functions. Those are decreasing, these are increasing because these are the functions of the radius. So instead of considering at infinity, the lower order at infinity, we need to consider here at 0. So yeah, haven't. Yeah, we assume FA to be finite. When it is finite, then this satisfies. So yeah, so this lambda of psi is limit x going to 0 log I x by log x. Okay, so this is the theorem. I'll just see how, let's see first how it works out for rationals. We have already seen that all these WDS properties holds with radius function as 1 by q square. So q is rationals and R of p by q is 1 by q square. Then in this case, what is f of A? So for A in the image of the radius function. So A is like 1 by q square. Then what is f of 1 by q square? We are looking at all those balls whose, all those rationals whose radius is 1 by q square. So those are exactly all those rationals with denominator q. And so we want this So we have these rationals whose denominators are q, say p1 by q, p1 plus 1 by q, so on. What is a supremum of R such that these are the balls around them are disjoint? So this distance is 1 by q. So you take 1 by 2q, balls of radius. So this distance is 1 by 2q. Then these are all disjoint. Yeah. So f of a here would be 1 by 2q. And so in case of Boucher's theorem, this x squared psi x is non-increasing. It's equivalent to in our theorem psi of x by x is non-decreasing. Because for us, yeah, I'll just make this a bit more clear. So for us, the W psi is this set, right? W psi QR is this set, x in x, such that distance between x I is less than psi of R of psi for infinitely many psi. And in case of reals, so W of psi, this is a set x in R such that mod x minus p by q is less than 1 by q square. Sorry, is less than psi of q. So I think it's better to write this function as phi, maybe not psi, here everywhere. So let's take phi. So we have psi of R of psi. We want this to be phi of q. And in rationals, R of psi is 1 by q square. So our function psi and this function phi are related by this. Psi of q square is phi of q. So when you ask for psi of x by x, when you ask for q square phi of q, this is phi of q by 1 by q square. And phi of q is psi of 1 by q square by 1 by q square. So this is psi of x by x. So q square psi q is non-increasing, is equivalent to psi x by x is non-decreasing. And again, this sum being converging is equivalent to this sum being converges by just putting f of q 1 by q square as 1 by 2q. So this will give us this result. And okay, I'm running out of time again. In the exact setup, only in real line the problem is solved, but in simultaneous approximation, it's not known, like in Rn. Our result also does not give any answer in that case, because the well-separatedness property will not hold there. So if we take in higher dimensions, Rn, then the radius function will have to be, so say let's take R2. So that countable set will be of the form P1 by Q, P2 by Q. And from the Dirichlet theorem, the radius function have to be 1 by Q power 1 plus 1 by 2. And with respect to this radius function, the separatedness property will not hold anymore. But there is another corollary of our result in another direction in the hyperbolic setup. So we can think of the approximation of reals by rationals in this way. So we have the upper half plane and SL2Z acting on it. And we have the boundary of this space, which is R union infinity. And then we have the orbit of infinity under the SL2Z. So this action is by Mobius transformation. This is set of all rationals. So the approximation of reals by rationals can be thought of as approximation of points in the boundary by the orbit of a discrete subgroup. So in this setup, another place where we can apply this theorem is one of the corollaries is, let we take any rank 1 symmetric space and gamma is a lattice and which acts on X isometrically, properly discontinuous, and non-elementarily. And then we look at the boundary and we have the fix a point in X, we have the visual metric and we have the measure on the boundary, the Patterson-Sullivan conformal density. So we have the measure mu X. So this turns out to be all-force regular in this setup. And also the annuli are non-empty, all the annuli. And in this case, the analog of rationals and the radius function is given by, take any, let xi be parabolic or loxodromic fixed point. And the analog of rationals is given by orbit of this point under the lattice gamma. And the radius function is given by, so take any element here, R of G xi is defined to is some constant depending on the point X and times e power minus rho X G prime X. Rho is a metric on the symmetric space we started with, and G prime is the coset representative of G gamma xi, which minimizes the distance from X to G gamma xi X. So with respect to this radius function with on Q, one can show that this satisfies WDS property, and we have alpha's regularity, annuli being non-empty, so we can apply the theorem in this setup. I wanted to give an outline of the proof, but I don't think it's possible now. So yeah, I end my talk here. Thank you.
Thank you, Prasuna, for the talk. Are there any questions or comments? Okay, if there are no comments or questions, let's thank the speaker once again.